So, good morning. Time again for quantitative big imaging, and today we are going to look into segmentation, or at least starting and working with the segmentation. And first, a little bit outlook, what we are talking about. First, motivation, then some qualitative approaches on how to work with the images. Also, how the images are actually formed, at least one example of it. Then we're going to look into the thresholds and how to first approach what a threshold is. A little bit implementation, not so much, and then round off with morphological image processing and looking at the partial volume effects that can appear in the images. As usual, we have a bunch of modules to load. Today there is not so much special that's new. Maybe this scikit image morphology is going to be more used in the second part today. Otherwise, this is a little support module that I wrote for nicer plotting. Some nice tools are in there if you want to use them. Yeah, so in principle that is it. And typically we have some kind of image, but mostly it's not really two-phase, it's more than that. So the two-phase would be that you just have some void and some kind of body, whatever material, could be a bone or some cells, or in material science, some metal piece, for example. And mostly we have something that varies with some gradients. So here, looking at the cortex in the brain imaging, it's very hard to actually identify it. So the physician can certainly identify where this region is, but telling it from the images and the intensity information alone may not be that easy. It's just maybe subtle chains in gray levels, or even just a regional or structural information that is needed to find it. And well, there's some reading, and well, as usual, John Ross has a lot of topics around this segmentation and thresholding. One tool that we're going to use is the ROC curve, which I'll come to later, and then there is also a video about how it can be implemented, and this is the repository which is related to this talk. So, first of all, why do we want to do experiments? So we usually want to have an hypothesis that we want to test and work with, and with imaging, it's often that you can actually see the things directly with the bare eye, so you can easily get a qualitative information from it. And sometimes you can actually, if you have few samples, the qualitative statement may be enough, but it can also be that you want to explore. You have something new and you don't really know what it's buried inside. A typical example that I came across was we had some old bronzes from pre-Roman times, and they want to know how they were cast, or seeing how they were made up. And we didn't know anything about these. They were made 4,000 years ago, but still, with the imaging, we could see that there were bubble formations in different regions, and with that, from that they could deduce something more about the casting technology that they used 4,000 years ago. But mostly, we want to test some kind of hypothesis, like we want to have statistical claim in the end. So, for example, does the temperature when you bake have an effect on the bubble size, or does the kind of yeast have an effect of the bubble size? How a specific gene is important for the formation of a cell shape, or does some canal volume improve or make the bones weaker? And in batteries can be, for example, some kind of conclusion around lithium migration. Here is some kind of granule as shape as an effect on the life expectancy. So there are many applications around where you can set up a hypothesis and try to find out. Imaging is one way of doing it, and that is what we are talking about here. And so what we first need to do is we need to acquire sometimes quite a lot of data. So in this example, we have 56 gigabytes of data per sample, which is more than most laptops have. At the time when this example was made, it was even way beyond what a typical workstation could carry. And even today, you have to make some extra investments to have a computer that can take the whole image at once. Then we do some filtering and pre-processing, which I have talked about previous lectures. And maybe many hours later, CPU performance has improved, so maybe now it's just a few hours later, but here is written 20 hours later. We still have 50 gigabytes of data, but it's less noisy. Or maybe we even have the double, because we went from 16-bit or 8-bit up to 32-bit, because we need to do number crunching on floating point data. So it's really, the data can grow quite fast. So we need to reduce it. And one way to reduce it is actually to identify regions, and with that we reduce the bit depth. So for example, if we want single numbers of like volume fraction, cell count, average cell stretch, cell volume variability, we can actually reduce the data quite a lot to come down. And this is what today's lecture is about. So segmentation is, in simple terms, that we identify relevant regions and tell the rest is not relevant. In some cases, we can even reduce it to a bi-level image, so we only have foreground, background. And then we have a quite radical change. The way to do it is often not very straightforward, but use the rule that simple solutions are usually the right one. Not always, but it's worth trying it, because the simple solutions, they are very easy to apply. If that is sufficient, well, go for it. And today I'm more talking about the concept of setting a threshold to achieve these bi-level images. And next week I'm going to talk more about algorithms and techniques, how we can automate this task. And it's often not so straightforward, because we may have unknown data. We don't know really what is our ground truth. And ground truth, again, is a very important thing to talk about. So, looking back to what we did, we had this system where we wanted some image. It's pulled through the imaging system, and out comes some pretty bad condition of the image, and then we need to do some conclusions about that. And we apply some kind of filter, more or less good. And let's see if I can bring, yeah, I can. So typically what most filters that are reasonable to work with do is that they improve the image so that most of the image information is actually relevant information, but there may be still some noise, because you can't filter too hard, because then you may lose relevant features. A bad filter would, in principle, enhance the noise and suppress the real information, so stay away from those. But that should be already tested. We had our test procedure, how we can see if signal-to-noise ratio is improving. We can check before, after, with simulation techniques, etc. So, what can we get from an imaging modality? I'm actually quite a fan of rubber ducks. So in this case, I put a duck in the beamline X-ray, and I got this image. And looking at it, we can describe something. We can see that there is, for example, so the qualitative information. You can see that there are some batteries, some electronics, and then can also see that it's hollow. So we can see that there are some different features in here. Can also look at the histogram. We can see that there is a lot of background, so it's very narrow, so we know this is really the background. We can see then for the duck itself, we can see that this is probably the rubber part, and then down here you can see the contribution by electronics and battery. So that is possible to see from a radiograph. What we can do also, we can, for example, trace the shape of this item and do some conclusions around that, but then we already start measuring. And how you approach this segmentation is, if you remember back to first lecture, we have different approaches depending on your background. If you have a background where you come from you want to have do the experiment yourself, so maybe you are a material scientist or in medical, have a medical application, then you know what you're looking for and you're segmenting and working according to that. Then if you have the computer vision approach, then you have a big bag of algorithms and techniques, and you start by applying these and see what you can get out of the image. In the end, you still need to talk probably to the experimentalist or an expert to really get out the information, but the approach is more that you are looking to your bag of tools and apply them to the data. The deep learning approach really requires that you have had someone sitting down working with the data to tell you what is the truth in this data, and then you let the system train and learn, and finally you will have a machine that can segment the images. So this one doesn't really require much from specific domain knowledge from the person who does the segmentation, but needs more to know about how to put together the program and the networks to do the learning. Yeah, so here we can see we have different approaches. So the experimentalists are going more model-based, and computer vision and deep learning, they are more looking into the results, so are really depending on having a ground truth. The approach of the imaging system is we have some kind of source that does some excitation. Could be X-ray source, could be ultrasound or something else. And this goes through the sample, and the interaction between this signal and the sample gives some response, and this response is then captured by the detector and can be reduced into something like this. We have a system, we have a stimulus, and we have a sample, and then we get the measured signal. And this can then look something like this. So we have the ideal profile. Sorry if it's a bit dark today. And then we have the interaction between the propagation going through the sample and also the beam profile. In this particular case, the beam profile is a combination of what the X-ray source gives us. That gives some kind of intensity gradient. And then we have the stripy parts, which is the amplification of different detector segments. And that's a bit combined in this case. Then there is a detector bias, which is in principle a way to handle the dark, the thermal noise in the electronics. So it's called dark current bias. And together we measure some image as a combination of all these four. Look at the profile across these images. We have first the beam profile, which is pretty flat. In this case, sometimes it can be really quite intensity focused towards the center. That depends on how the source is configured. Then we have the detector image, what the detector sees. And we also have the sample image, and in this case, the sample image I multiplied by quite large factor because it was normalized in this case. And you can see that there are differences in particular, not so much. In these regions, you can see maybe some fluctuations, and they are caused by the beam profile, and also this difference in intensity is also caused by the dark current contribution. So in absorption imaging, which is what I work mostly with myself, we usually work with Beer-Lambert's law. So it's the universal attenuation law, which has, in principle, consists of some kind of source intensity, and then you have a decay in intensity caused by a factor alpha and the distance, travel distance within the sample. And this alpha is called attenuation coefficient. So the thicker the sample is, the more the beam is attenuated. And of course, it's complex system. So first of all, alpha depends on the spatial position. In this case, I just use X and Y, but we also have Z. Of course, we have 3D data, but not only, it also depends on which elements or which material. It depends on the density, and can even depend on the excitation energy. So there are many factors involved in this alpha, and usually we reduce it to a single number which has a spatial distribution. So this dependency on wavelengths is something I'm going to show you examples of in a few weeks. And that can actually also be used as one factor in the evaluation. So let's look at some transmission image. There's a little bit of code, but in principle what we have 3 different materials, alpha 1, 2, 3. And they have attenuation coefficients, also 1, 2, 3. And there is some noise spread within them. So we just simulated here with a normal distribution with different sigmas. That is put together now in a data frame, and then we can present it. We have different alphas here. So the alpha is fluctuating, and the reason why it fluctuates is one is that there can be different density variations within the material, but it can also be because of the noise distribution of the source. So the source is, in this case, some kind of photon source. So it's an event type of source, and then it would in principle be a Poisson distributed, but here I simplified it by using normal distribution. So there are always some degree of noise. More noise can be added by the detector system, that the camera has some noise effects. You can have readout noise, you can have also discretization noise if you're going really precise. So there are quite many noise sources in it. But let's start with this table and looking at what we have when we plot the intensities. So here we have the alpha value, and here we have the intensity measured at the detector. And you can see, thanks to the attenuation law, we have this decaying curve. And what we measure are different intensity distributions. You can now see they are a bit skewed. But you can see that there is a histogram for each material. And if we flip it around, looking at only the attenuation coefficients, there is a different spread here. And it's not pulled through the exponential. And when we measure transmission images, and also other images actually, also I would say this applies also to microscopy, we have to compute the transmission image because that is the one that can tell us something about the sample. And the transmission image is technically computed as, basically it would be just the ratio between the measured and the incoming intensity, but we also need to subtract the bias of the dark current. So in principle, what we get is we have the measured image minus the bias, we have the source image minus the bias, and then we can normalize it. And once we have normalized it, we don't have any structures anymore in the image, and the value should be between 0 and 1, because the intensity cannot be increased more than the illumination itself. Yes? How? How you get the bias? You measure it. In principle, you switch off your source and make an image. Even better, you put even a lid on your lens, then you can get your dark current. There are different levels, but the first thing is turn off the source. And then you don't have anything that can give you other signal than the detector itself. That is a simplification because there can be, for example, detector lag, that the scintillator may still afterglow, and if you do it too fast after, then you would get some afterglow effect. So you always need to wait a little bit before you do this dark image. Or do it the very first thing you do. Yeah. Yes? Yes, that depends on detector technology. There are specifications for it, so you have to do the dark current with the same exposure time as you do the image with the samples, because there is an additional count of electrons coming into the detector when you have longer exposure time. If the dark current is fluctuating during your measurement, then you should buy a new camera. Because that's not good. Now, it should definitely not. The dark current should not vary. So if you set it for one exposure time, you should expect that it gets you, say, 300 gray levels plus minus 10, or something like that. That you must rely on. Otherwise, it's time to change. So a little example of an image. So this example is about mammography. So we do an X-ray, and we have here again the X-ray source. We have the attenuation law, and what the detector measure is again this integral. And now I actually have it in 3 dimensions. And what we can say is that the attenuation coefficient should be, in this case, approximated being more or less constant. And then we have some thickness. And the attenuation coefficients here are set to 0 for air. There is no attenuation in the air. And the breast tissue is set to an attenuation coefficient of 0.01. And as we are now flying through the beam, with the beam through something that is not perfectly constant, we change this sum of materials into the original is that you have a line integral, but now we reduce the example to discrete, so we have either air or we have breast tissue. And let's make a simple model. So this is a half sphere that I cut out. So I use this ball structure element and take half of it, and then we get this structure here. This is not really true actually, because now this is a volume image, but in mammography they take 2 plates and squeeze, and then they have constant distance through the breast. So this is not a fully perfect model of what's actually happening in mammography. Then we say we have the breast alpha is 0.01. We have a pixel size of 0.1, centimeters. The unit of the attenuation coefficient is typically per centimeter for some traditional reason. So therefore we say we have a pixel size is 1 millimeter, so here it's set to 0.1. The volume is then, in principle, multiplying the breast alpha with the mask, and then we compute this transmission image from that. And the result is we get an image, which would be the radiograph from the side profile. And looking at that, we have the highest intensity here. So we have, it's a flipped column up here. It's a bit confusing, but it's more like the radiograph as you would expect it from the film technique. And so then you get this kind of profile if you look along this red line. Looking at the histogram, we have a histogram with decaying numbers here, which correspond to the breast pixels. And then we have a very large peak here, which is the background in the image. And now we want to know the thickness of this image. And what we do is we reverse the Beer-Lambert's law. So we have first the logarithm of the negative logarithm of the detector image and divide it by the known attenuation coefficient. And out comes then the thickness in centimeters. And of course, now just to remind you, now the color scale actually flipped. So this is the thickest part, so it's apparently 10 centimeters at the brightest, and then you can see it goes down to 0, which it is here at air. And of course, also the distribution of thickness is flipped around in the histogram. So, and if we're looking at the thickness distribution, it's now not a half sphere, but more something that is projected going from 0 up to a maximum value. So, the idea behind doing a mammography is to detect if there are any breast cancer, and that would be that there is some kind of anomaly. So that in turn means alpha is changing on a certain spot. And that we need to see. And the problem is that in a radiograph, you can't tell if it is thicker or denser. And that is the problem when you do radiography to identify. So let's include this little lump here. So I added a little extra sphere. You can see it on all the slices in the volume. And this one we can also visualize and see what happens. First, we see the detector image in the radiograph, but there is actually something. And now is the question, what does this something actually correspond to? Because you can't say from this image if it is just a different thickness or if it's something that has a different attenuation coefficient. You can see that, of course, that there is a difference in the histograms between original and the one with a lump, but still you can't say what it is. Actually, to really detect it, yes?
When you mean a different thickness, you mean how much tissue is there in the...
Yes, yes. So, in principle, what you have is, if it says that you have thickness equal to 1, then it could be that it corresponds to, the transmission has a certain value. And that transmission could be either that you have a thick thing or that you have a combination of two materials that gives you this different thickness. And that is the ambiguity that you can't tell. Is it caused by a material mixture or by more material? And that you can't tell from the radiograph. For that you need to do a tomography to tell the difference if there is a region of something else.
Even if we squeeze the breast so it has...
then you have the a priori, of course, then you have the a priori knowledge that it should be this thickness, and then you can reduce that from the equation. And then you can say really that there is, yes. But then you have taken out the thickness and or put the thickness as a priori. Then it works, yes. And that's actually the trick they do. Yeah, and then I compute the thickness from the same, using the same equation as I did before. And again, you can see that there is a difference between the histograms. And looking at it, if you would look at the profile, it would look like this. It's not really natural, so we would probably, by common sense, conclude that this is something that shouldn't be there. But computationally, we can't say we have one variable too little to tell if it's really a changing shape or is something that is thick, denser inside. So what we need when we do this image formation, we can mostly not use the images directly. So we need to do some kind of normalization to get there. And the information from pure transmission images are not easy to interpret unless you have reduced the information, for example, then of the thickness. And this is something I do a lot with my colleagues in soil physics. They look at the water content within soil profiles, and then they also have slabs of a known thickness, and then we can, from that, we can deduce the water content in the data. So now we get to the segmentation, and first of all, we want to convert some kind of complicated number, this transmission value, for example, or even RGB value, going even further, maybe even a spectral image, where we have, say, 100 or even 1,000 spectral bins. And we want to reduce that into a very simple selection, sometimes even between just true and false, or sometimes in a few very limited classes. So if we go for the true-false case, we reduce our data from 56 gigabytes per sample down to 1.75 gigabytes, and that's much easier to handle in some processing situation. So looking at a very simple image, we have this cross, and it's a bit noisy. And yeah, now we want to put mark out this cross itself under this condition of the noise. And looking at the histogram, we can see that we have maybe two bumps here. So we have one part here and one part here. So this would be the background, and this would be the cross itself. And now we want to identify where the cross is, and that can be done with a process called thresholding. And well, what would you do to identify where the cross is? Any idea? What? Look at? So about here, you mean? Put a threshold here. Yeah, so in principle saying everything that is less than, in this case, 0.5 belongs to the background, and everything that is greater would be foreground. And that's quite a reasonable choice in this case. And let's see what happens. So in this case, I just do 0.4, which may not be the best choice, but you can see here now that by doing that, I put it here, and these are the thresholded pixels. Looks pretty good, actually. Interesting. I would expect to be some misclassifications, but apparently this one did quite good at 0.4. And now we can also explore what happens if we change our threshold over a range. So here I have a couple of more or less good threshold values. And looking at those, we can see that for a too low threshold, we certainly get the cross, but we also get a lot of pixels out in the background, which we don't want. And it only turns out well if we are in the range of 0.42 till 0.58. Then we have a good cross. If we go even beyond that, then we start losing the cross. So then you can see here are some pixels that are not segmented as a cross anymore. And that case turns even worse when you go to 0.9. So it's important to know where you put this threshold. Today I'm not giving you any algorithms for doing it, but I'm showing more the concepts of the idea of the threshold. So looking at the real image with cells, we have this image with some cells, and all the black dots are cells. And the histogram looks like this. So there is no obvious point where we can put the threshold. So now is the question, what happens if we set different thresholds? And this is a situation that often happens when we have something that we want to see, which is underrepresented in the data. Then we have a very large peak of the background, and then somewhere around here is a threshold for what we want to see. And if we now try different thresholds, so here I have thresholds from 100 to up to 200, and the effect you can see is that you get pretty many of these cell dots, but you can also see that they are growing on one side, and some are getting more around this corner. It's getting a lot in this corner, in particular here at 200. And the reason is that our illumination in this image is not perfectly flat. So this image was probably not normalized. So we have a diagonal gradient, and that diagonal gradient has an effect on the image segmentation. So what we need to do is actually to do some preparation to correct for that. Then we can go even further, looking at vector images. So we have the intensity and also some orientation in x and y vector. And that can look like this. Then we have, let's see. So, so we have here, we have x, y, we have intensity, we have x vector, and we have y vector. And on the x-axis, the same values. So this is a so-called pair plot, where you can look at different values in your data in an overview manner. So what you have in the diagonal is just a pure histogram of the data itself. And then you have combinations of the different. And you can see that the x and y vector, they combine pretty well. So apparently this is a circle. And then there are some intensities of different kinds. You can see that there are some sine shapes, for example. So this can be a very good way to see, identify which pairs of information are more useful to look at together. Then we can plot it as a vector field. So here is a quiver plot where you can see all arrows are pointing outwards. And now we want to, from this, we want to segment a certain direction. So for example, when x and y are greater than 0.25. And when we segment that, you can see here that the yellow region is what we segmented. So you can actually segment on each individual point, individual vector, but mostly it's a combination of the two that brings you to the answer. And looking at other things, yeah, it's just a different way of looking at it. So this is a bivariate histogram, and then you can see also where these thresholds are coming in this data set. And what we also can do, we can also look at the dot product of different directions and setting that. And then we can looking at scalar products. So then we can say which angle we want to segment. So if the angle is greater than some theta, then we set it to 1, and otherwise we set it to 0. And I think there should be something here. Let's see. No, nothing. No. Okay, so that was the first part. And it's time for a break.